Welcome back, chemistry fans. Today we are going to do Unit 13, Topic 3. We're going to try and get ourselves into this discussion of what is a pH today. So let me share my screen and we will jump right into that discussion. What the pH scale is. You have talked about it since elementary school. It's this scale that runs from 0 to 14, and the lower on the values, that means it's an acid. The higher on the values, that means it is a base. Right smack dab in the middle, 7, that means it is neutral. What you haven't thought about is what it's actually measuring. The pH scale is actually measuring the amount of hydrogen that is in the solution. The more hydrogen there is, the more of an acid it is. This fits the definition that we have talked about. The less H, the more it tends to be towards the base side of it. And if there is an equal amount of acid particles and OH particles, which are present on the pH scale, the base side of it, well, then it's right there in that neutral side. Well, we need to understand how to calculate that pH value so we can put it on this scale. So that's where we're heading here. Now, before we do this, we have to understand, again, reacquaint ourselves with the term dissociation. Dissociation means that the material is 100% separating into ions. That's a key feature for pH to work. If we have some of the acids that are resistant to separating, to dissociating, well, then we will not have a good exact number, because if we have a certain amount of the acid poured, but not all of it dissociates, well, then we don't have all the H's available to measure. So that's going to change our pH. So we got to keep that in mind as we move forward in this discussion. So how we differentiate some that do dissociate and some that don't is we're going to give it a relative term. It's either going to be a strong acid or it's going to be a weak acid. So notice in the images, strong acids are going to be defined as materials that dissociate from one another 100%. If I have 3 HCl particles, it is going to break apart into 3 H's and 3 chlorines. But notice over on the right, if I have 3 of these acetates ions or acetic acids, notice only one of the 3 is going to separate. Well, that means its pH is going to be lower, even though they might have the same amount of material. Potentially, only a smaller portion of it is going to be available as an H. That makes this a weak acid. So there is a way to know by looking at it if it is going to be strong versus weak. So reiterating here again, pH is very low if you are a strong acid. The pH of a weak acid is sometimes a little bit higher, sometimes in the 3 to 5 range. The acid is going to completely dissociate and it's going to release all of its H's. Well, how do we know what is strong and what is weak? You're going to have a list of them. So this puts out right there 7 of them. I may expand this one here in just a second. No, I think we're going to stick with this 7. So these are the only 7 acids that are strong. There are dozens, if not hundreds, of weak acids available. So you're not going to ever have to memorize what is a weak acid. You are going to need available to know what are the strong acids. There are ways in which you can help yourself memorize it. If you look on a periodic table, HCl, HBr, and HI, they are all halogens. They're all on the right. And then you'll notice that the chlorate and the perchlorates, they are going to form strong acids. That just leaves the next 2, which is sulfuric and nitric acid. So if you can then put together that list, you would have it memorized. But here it is again. Now, just as well that there are strong acids, there are actually also strong bases, and there are 8 of the strong bases available. And they are a little bit easier to remember because if we think about them on the periodic table, sodium, potassium, lithium, rubidium, cesium, they are all straight in line on the first column. Now, it does skip for the strong bases, it skips magnesium and it goes to calcium, barium, strontium on that second column of the periodic table. So very easy to memorize these if you put just a little bit of effort to it. And again, what this tells you is these are the elements that, or these are the materials that will dissociate 100%. Everything else will not. So once we have that knowledge, we can now plug it into a formula for the pH. The pH is equal to the negative log of the hydrogen ion concentration. Now, the way it's written above, it's the exact same measurement. It's just that some authors may prefer to write it as H3O because you can't really have H's exist by themselves. They generally are associated with water, and so they make it heavy water, H3O. They make it hydronium. So if we have a pH scale that has this formula down below where we can solve for basically the power of hydrogen, well, there's just an opposite scale that is the power of hydroxide. So this scale, the POH, would be measuring how much base there is, where the pH scale is measuring how much acid. So if you have a low pH value, you would have a high POH value. And vice versa. If you have a high value on the pH scale, well, then you would be low on the POH. And so what this means is that if you add together the pH and the POH, it will always equal up to be 14. Always going to equal to be 14. So pH plus POH will always equal 14. So this chart here is just showing you how the two are related. It's very convoluted, but the bottom line is down here, pH and POH, they are related by 14. All right, so let's do a couple of practice problems. Need to get out a calculator and participate wholly with this one, fully with this one, so that you can understand how to utilize the log button on your calculator. So the formula for pH is negative log of the hydrogen ion concentration. This is a strong acid. It will dissociate 100%, meaning that that concentration is also the concentration of the hydrogen. So I have negative log of 8.9 times 10 to the negative 3. So plug that into your calculator. Negative log of 8.9 to the negative 3. And what you get is 2.05. No units on pH. Now let's go the opposite way. How would we calculate this as the POH? Well, you would do the exact same thing. The formula, however, is not hydrogen that you're measuring, it's the hydroxide. This is a strong base, so it is going to dissociate completely. So I can take that negative log of 6.4 times 10 to the negative 11. And what you get is 10.2. Now that's on the POH scale, which means that it would be actually very low on the pH scale, because we do the opposite. We do 14 minus this to find out what its score is. All right, well, now what do we want to do if we want to go backwards? If we are given the pH and we want to figure out what is the what is the concentration for this formula. Whoops, I'm going to actually change this to NaOH. I'm going to change that to NaOH instead of magnesium, so we know we're dealing with a strong acid. All right, so what we got to first do is reverse and turn this into a POH. So we're going to subtract 14 from the value that they give us, and that makes it 1.8 on the POH. Then what we're going to do is we're going to do the inverse log. If you notice on your calculator, the inverse log is 1 times 10 to the negative POH. So what we're going to do is 1 times 10 to the negative 1.8. So put that into your calculator. 1 to the negative 1.8. And you get 0.016 as the concentration. So that's molarity. And we have one more example to do. Probably should have left a little bit more room. So you are given a pH of 2.44. What is the concentration of this solution? So we'll do the exact same thing. We'll do 1 times 10 to the negative 2.44, because this time this is an acid, so we don't need to flip it. So we're just practicing one more time. 1 times 10 caret negative 2.44, and you get 0.0036 molarity. Okay, we're moving on to our last topics now. So we've talked about strong acids. Well, now we have to talk about weak acids. How do we measure the pH of a weak acid if it doesn't completely dissociate, if it doesn't completely break apart? What we're going to have to rely on is something called a Ka or a Kb. The A stands for acid, the B stands for base. What you have in this is a ratio of products over reactants. So what we're going to do in these cases is you will be given this concentration to start with, and you will be given the ratio of the dissociation. It's going to be a decimal. What we won't know are these two values here, but because they will dissociate at the same rate, they will be the same value. So I can make them both X's. So what ends up happening is that we'll have X squared over this molarity that's given to you equal to some decimal. So then all we have to do is a square root to solve for it. The exact same principles hold true for Kb. Instead of solving for OHs, instead of solving for H's, we'll be solving for OHs. Now, if for some reason they give you one of the Kas and they want you to solve for the Kbs, they are related by the fact that Ka times Kb is equal to 1 times 10 to the negative 14, just like pH times POH is equal to 14. All right, so let's do one more couple of examples here, and then we're going to move on to the next topic. Okay. So we've got, in this scenario, we've got a Kb value, and they give us the initial concentration. So the formula, again, was Ka is equal to the concentration, we got Kb, boop. Kb is equal to OH times what else is left over, which is the Al part, over the AlOH, and it happens to be 3. Okay, so what we're going to do is we're going to simplify and say that those two values up here are the exact same, how they dissociate. So it's going to be X squared over the concentration they give us is 5 equal to 1.4 times 10 to the negative 5. Now we've got algebra that we're going to simplify. So I got 1.4 to negative 5 times 5 equals 7 times 10 to the negative 5 equals X squared. We just do the square root. We do the square root, and it will tell us that the X, which is the same thing as the hydroxide ion, it is equal to 0.008. Now, that's the concentration. That's not what we're looking for. That's just the concentration. So now we have to plug this into the formula to solve for the pH. So remember, pH plus POH equals 14. So what we're going to do is we're going to take the pH, which we're looking for, and we're going to say 14 minus this value over here. It's going to be a very large value. 14 minus that is 13.992. That's my pH now. Oh, sorry, that's not. That's what I need. So now what we got to do is convert this into a POH. So I've got negative log of this hydrogen hydroxide ion concentration. So I've got negative log of 0.0084. This makes more sense. Is equal to 2.08. Now I subtract that from 14. And now I get 11.92 as my pH. Okay, that's a lot of work, lots of steps to get yourself to that point. Now, in the next section, what we will talk about here is what happens if they give you something called the pKa. So if you recall, Ka is a ratio of how much it dissociates. It's a percentage. Well, what if they do it instead of giving you this decimal? What if they turn it into a log value? All we have to do is reverse it, just like we did pH. If they give you the concentration, we do the reverse of it. So we've got an example problem here where we have a pKa, which is equal to 10. So what we're going to do is we're going to reverse that value and turn it into a Ka value. And then we can plug it into our pH formula. So what we're going to do is negative log of 10. Because we have a pH. And so what we're going to do, is we're going to do the 1 times 10 to the negative 10. And what you end up with is 1 times 10 to the negative 10 is my constant, is my Ka value. So now what we're going to do at this point is we are going to then try and plug this in to solve for a pH. And there is this formula called the Henderson-Hasselbalch equation. But since there is a value missing, let's go ahead and say that it is the C6H5O. Let's say that it has lost the hydrogen. It has a concentration of 0.02. Okay, now what we can do is we actually can solve this using the Henderson-Hasselbalch equation. pH is equal to pKa plus the ratio of the base, which is the material that accepts the hydrogen, 0.02 over 0.1, the acid, and then we'll solve that, and that will give us our pH, and that was what was supposed to be on the next slide here. So we will do that right now. So we'll do the log of that. Okay, now this is probably something that we will cover whenever we get to the buffering topic, which is last, but it's being introduced right now. So I will go ahead and just finish this problem. I don't anticipate doing this one in class. Plus my pKa is plus 10. So I've got a 9.3 as my pH. My pH would equal to 9.3. Okay. So again, I think this probably is a little bit of a stretch for where I wanted to take us, because I think I wanted to cover this with the buffers, but it's introduced, it's talked about. We will see you guys soon. Thank you so much for your time. It's getting a little heavy, I know. Sorry. Thank you so much. Farewell, and do your homework now. Bye.